this video, we will learn about the different types of radioactivity. Radioactivity is defined as the emission of ionizing radiation or particles caused by spontaneous disintegration of the atomic nuclei. There are three different types of radioactivity. There's alpha radioactivity, which affects the nuclei because it takes away 4 from the nucleon number, which is made up of protons and neutrons, and 2 from the proton number, which is the atomic number. Beta particles are electrons, so they do not affect the nucleon number or the atomic number because they are outside of the nucleus in a cloud, in the electron cloud. Gamma photons, which are highly charged particles, are also on the outside of the nucleus and therefore do not affect the number of protons or neutrons. When looking at radioactivity, there are 3 rules of decay. The first rule is that the nucleon number is conserved. The nucleon number, A, is made up of protons and neutrons. So in other words, you could think of it as the atomic mass. The second rule is that the atomic number, the charge, because the atomic number is usually protons, which are positive charges, is conserved. So your letter Z is conserved. You can think of this as the atomic number that you identify atoms or elements with on the periodic table. And the last rule is that energy and momentum are conserved. This rule will fall in with beta and gamma radioactivity. First, let's take a look at alpha decay. Alpha decay states that the parent nucleus transforms into the daughter nucleus by decaying an alpha particle. An alpha particle is made up of 4 nucleons, which is your atomic mass. So 4 particles from your atomic mass and 2 protons. So an example of alpha decay is when we see uranium emit or have an emission of an alpha particle, which is helium. When we need to conserve the nucleon number, we take 238 minus the 234, and we conserve it with, it is conserved with the 4 particles that the alpha particle took away. When the alpha particle takes away 2 protons from the parent element, or the parent nucleus, it is conserved by the 90 protons in the element thorium. Now let's look at beta plus and minus decay and gamma decay. Beta minus decay converts a neutron with no charge into a proton with a positive 1 charge. However, you cannot just create mass, it has to be conserved. Your proton or your atomic number must be conserved. That is where the electron comes in. The nucleon number is not affected as it goes from 1 to 1, with the electron not contributing any mass, only a charge. Right here we see an antineutrino. Antineutrinos have no mass and no charge. So what is their purpose? They are there to conserve energy and momentum. So the final reaction is to take the parent molecule and lose an electron to beta minus decay and gain it in the daughter element. And to also always make sure we include our antineutrino to conserve energy and momentum. This is known as an electron with a negative charge, and beta minus decay is denoted by a beta with a minus sign. Beta plus decay does the opposite. It converts a proton into a neutron. To do so, a proton has a charge of +1. However, a neutron has no charge. Therefore, we use a positron, an electron with a positive charge, to conserve the atomic number. Once again, just like the electron, the positron does not affect the nucleon. The nucleon is conserved by the neutron. And here we have a neutrino, which serves the same purpose as the antineutrino, to conserve energy and momentum. So therefore, we get the reaction for beta plus is that the parent atom will transform to the daughter atom by losing the charge, because you're going from positive to neutron, or proton to neutron, and gaining it with the positron, as well as having a neutrino to conserve energy and momentum. Beta plus decays are denoted by beta with a positive sign, and positrons are electrons with positive charges. Lastly, we have gamma decay. Gamma decay is when gamma rays are emitted when a nucleus is in an excited state, making a transition to a lower energy level. So as you notice, we do not transform the element. It is the same element with the same nucleon number and atomic number. The only difference is that we have a gamma to conserve the energy that was lost, because it's making a transition to a lower energy state. So if we were to use this practice problem as an example, we would say that in the first one is bismuth undergoing alpha decay. We know it is undergoing alpha decay based on the fact that a helium atom is present. So to conserve the nucleon number, we will take 212 minus 4 and get 208. To conserve the atomic number, we will take 83 and subtract 2 to get 81. Now to find the daughter element, we look on the periodic table. We look for the atomic number 81, and we find that at 81 is thallium, Ti, or Tl, excuse me. So Tl is thallium. For number 2, we have krypton undergoing beta minus decay. We know this because in the problem, the electron has a negative charge. So therefore, it is adding a negative charge, and it adds no mass. So in efforts to conserve the nucleon number, we find that the daughter element must also have a mass of 95 for their nucleon. However, in the protons, since the 36 protons lost one to the electron, we must add one in the parent, or in the daughter element, to conserve. So we will get 37. And when we look at our periodic table again, we find that element 37 is Rb, which is rubidium. Problem 3 is alpha decay, and we know this because we see the helium element. So we would need to work backwards to find the parent element. Since we know that cesium was the outcome of this alpha decay, we are able to add the numbers going from right to left, since all of our nucleon and atomic numbers are conserved. Therefore, we will end up with 144 and 60. And when we look on our periodic table for the element with the atomic number 60, we get neodymium, which is Nd. Problem 4, follows the same pattern as number 2 did because it again is a beta minus decay because it has an electron. So when we start with boron and we put it through beta decay, we conserve the nucleon number and we compensate for the loss of charge from the electron. So we get 6, which on our periodic table is carbon. With the beta decays, don't forget your neutrinos. So in this case, we will have the antineutrino, which conserves energy and momentum. We forgot to add it in number 2. Okay. Now number 5 is asking us to figure out what type of decay occurred. So we start with thorium and end up with radium. Now we can figure out what type of decay happened based off the nucleon number and the atomic number. So we see that the nucleon number lost 4, so we will add 4, and that the proton number lost 2, which we can identify as an alpha decay. Lastly, we are again trying to find out the parent element. So we are given that we have nitrogen going through a beta minus decay. So we can add from right to left to find our parents. So if we were to add across the top, we would find the nucleon number to be 14, and 7 minus the 1 electron is 6. Therefore, we know that this is carbon.